So once again, welcome everybody to Improving Product Design with Onshape and SimScale, session number 2. My name is Paweł Sosnowski and I will have the pleasure of being your host today. I'm the lead sales engineer at SimScale GmbH, and this is the presentation. A short agenda for today. At the beginning, we'll have a recap of previous session, and further, we'll move to the clue of today's topic, that is the setup of thermal simulations and first thermal analysis on the geometries that we prepared last time. After that, we'll take a look at the troubles we can find when we prepare the geometries in a certain way, and we'll use the existing design in order to make modifications to it such that it will be more suitable for simulation purposes. From there, we'll make a second try for our thermal analysis of a PCB board and obviously improve the design, including some additional parts. We'll end up the session with a Q&A. Now, some technical remarks. Anytime you will see that my voice disappears or the screen gets out of sync, I would highly appreciate if you would raise your hand and start typing to me, "Hey Paweł, there's something wrong," so that I can try to address it and begin and move the presentation in a proper way. When it comes to questions, I will try to answer them as we go. At the same time, there's quite a lot of us again. I'm really happy about that, and we also see some new faces. So if there will be very many questions, I'll keep them for the Q&A session. So please be patient. So now, just to confirm that everything is good and we are all okay with the technique and the technology, I would appreciate if you would start raising your hands just to check that you can see the screen and the agenda. Great, I see first hands appearing. Awesome. So I will take this as a notice that we're ready to go. Okay, let's make a short recap of the first session from last week. We had a discussion about the approach of design, which involves the computer-aided engineering, where we have an additional loop in the process of developing a product, where instead of building hundreds or tens of very expensive prototypes, we will include a simulation to perform numerical experiments on the design, and this way be able to make engineering decisions on our, let's say, virtual approach, this way saving money and time. Let's take a look at the short recap of the SimScale approach. So how do we make those simulations? Because I assume that most of you already are pretty good CAD designers and are familiar with Onshape. So from the SimScale part, we're also providing you with a web-based application that allows you to run the simulations only using a modern web browser with WebGL enabled, and gives you access to supercomputer power of clusters where you can run your jobs, perform the analysis, and take your engineering decisions, including them in your CAD designs on Onshape. Now, that was a really short recap because I know that you're all anxious to see the future development of the project, and let's talk a little bit about it. The best way to learn is always to take a real-life example, and in this case, we had a virtual job of our partner, business partner, who said, "Hey, I have a PCB board and would like for you to develop a box that will cover it in some pretty dusty and vibrating place." That is where we made the analysis for finding out the eigenmodes for vibrations of the box and improved a little bit the design. Today, we will extend the interest and start looking at the board from the thermal point of view and seeing how does the energy is being moved around and where there are some hot spots, or if we can improve the design of the board itself. All right, so what is it that we're going to solve? I need to give you some kind of a scare. So a nice partial differential equation where we'll be seeing the evolution in time of temperature. This is a very nice image taken from Wikipedia. I really like the way that the 2D temperature is being represented. How does it move around and dissipate? All right. So we're ready to go. We have the clear scope of our project, and we would like to use the geometry that we prepared on Onshape last time in order to run the thermal analysis. And this will be the first step. Oh, I jumped too fast. A sneak peek for what's going to happen shortly. Let's say that we are in our dashboard after logging into SimScale, and we would like to find the project. Right now, you can also do that. Just go to public projects and type SimScale Onshape webinar. Obviously, you need to be better at typing than me. And then we have first session project. We can just copy the name and then go back to public projects and look for the second session project. It is over here. Whenever you would like to give yourself a try and play a little bit, change some parameters, or even use the CAD model, why not? You can just make a copy for yourself. And this is exactly what I did for this account, this demo account. So you just go here, find the project, SimScale Onshape webinar, and make a copy for yourself. After just a second, you will have a little thing appear here. I kept it private just not to make multiple duplicates. So I also highly recommend you to change the name, like my own try, so that we'll not have 3 billion of them appearing at the same time. Okay, let's open the project and see what is it that we have inside. Immediately, you can notice that the PCB board appears. This is what we'll be mostly focusing on. And the first thing that will happen is we need to make a mesh. So perform a numerical discretization of this little element. Last time we were more concerned about the box, but for today, let's focus solely on the board and leave the box for later, especially that we are dealing with the heat transfer in solids. In order for the heat to be transferred between one body to another, it needs to be strictly connected. In our case, let me just switch the view, the PCB board is a pretty good isolator. So any heat that would be transferred from it could not go through the legs into the box. Let's take a look at the box representation. Let's hide some faces. So in this particular case, the only way for the heat that comes from, for example, the processors or resistors to be transferred through the solid bodies without taking into consideration the gas around it, it would have to go through the whole PCB board and through those little legs over here and then be transferred here. Obviously, this would be a waste of computational time because we are pretty sure that since we have a high isolating material used for the board, the heat will not be able to be transferred through it. All right, so let's keep our view for the moment at the board and perform the first meshing. We had the geometry ready. We made the mesh. I already demonstrated it. So there we are. Each and every element has its own mesh. We could start hiding them so that we see how does the mesh look like. And now I will not spend too much time on describing of all these elements. We'll jump immediately to the simulation. The way you can always go back, import the project for yourself, or simply view it and see what kind of meshing did I use. In this case, it was parameterized tetrahedrization with some maximum minimum elements. A pretty simple thing. All right, and let's go to the initial run when we are making our job. Or let's even do it live and start a new simulation. I'll not give it a new name. Whenever you're performing a thermal analysis, we'll need to go to thermostructural analysis type. And you'll notice that there are two ways of doing it. Either you can use the heat transfer analysis, which will incorporate the Calculix solver, or you can go to advanced heat transfer analysis, which can also perform the stress analysis and expansion or contraction of the material due to the heat changes. This is performed by CodeAster. For this particular run, we'll choose to go with heat transfer since we're not concerned that the temperature changes will be big enough to make the stress appear on the board, or we're simply not interested in them. Again, we're jumping to the standard SimScale approach where you have your vertical setup of the simulation. We start going top to the bottom through the tree that appears on the left side. Let's choose the mesh. We would be choosing the models, creating some contacts. Obviously, it might be a little annoying to deal with the names of faces such as this one. If I select the face on the PCB board, it is called face group on face geo face 0. It's not the best name. So I could create a new set and give it a name. PCB to electronics face, for example. Now I will get a warning since I already created a set that is exactly like this one. In this particular situation, I have the PCB to electronics, which is this particular face, and let's pick volumes and hide the little bugger. And obviously, we need to also select all the faces that will be connected to the board itself. Keep in mind that every element, every volume, is a separate entity that floats inside the simulation space. So it's our job to connect it somehow to the board or between each other. In this particular situation, we'll use a contacts. This is another thing from our top to down approach. Add a contact. It will be a bonded contact. Yes. And now we're supposed to select the master entity, which will be the face on which we will be making we will be gluing other parts. So let's select the PCB to electronics. This is the face. Clear selection. And the slave will be all those little faces that I pre-selected earlier. So 33 little faces that are touching it. The general rule, whenever you're making contacts like this, is to have a coarser mesh as the master and also the bigger one to be the master in order to have a faster calculation time. All right. Further, we go down with our settings, nothing to do in the model, but we need to add materials. The way to define them is exactly the same way as we did for the model analysis. So we just have a similar approach, even though we are using a different solver. We need to provide the density and the heat conduction coefficient. Obviously, this would take some time, so I'll just skip that, and later we'll see the predefined simulation. Further, we go to set up the initial conditions and the boundary conditions, adding some. In this case, we'll be adding some volume heat sources. For SimScale, you're required to provide the volume heat source in the unit of watts per cubic meter. This can be a little troublesome when we're dealing with, for example, electronics. In order to do that, we know, for example, that there is a 1 watt of energy being deposed inside the processor. So how many watts per cubic meter is that? And you cannot easily find the volume of the thing. This is where Onshape comes to help, and the fact that we created our geometry inside Onshape so that we can simply go to our project. And again, it's a public project, PCB Analysis SimScale Onshape Webinar 2. You can go there, make yourself a copy, or simply view what was done. Let me just open it. We go to the assembly that we of interest and pick the part. For example, let's say the chip. Now that is selected, on the bottom right of the screen, there's this little icon that allows you to display mass properties of this body. And it will directly give you the value of the volume and surface area. If you were to add material to this little body, you would also see the center of mass and moments of inertia. This can be pretty useful to get the values. So for our case, obviously we have the volume. We just would simply need to take 1 watt and divide it by the total volume. Keep in mind that we are dealing with meters, cubic meters. So again, the proper unit conversion would be required. In the end, the energy that we would set for example, our processor number 1, the main thing here, we will add assignment and would be of a range of 25 to 150,000, I believe. Let's take a look at the simulation that was created earlier. So initial thermal simulation, PCB run, heat fluxes, processor, and yes, it was 250,000 watts, which will correspond to roughly 1 watt applied to the whole, 1.6 watts applied to the whole processor. Then, obviously, all these values are, I chose them arbitrarily for sake of the example. And if you would like to have a little more detailed analysis, I highly encourage you to make a copy for yourself and play around. So all the elements that are heated up are selected and given proper density of heat. And now the last thing is the cooling. Somehow we need to define where the cooling will happen. Obviously, it will be all the faces that are outside, except for the contacts that are hidden. And there will be one little challenge about this particular approach, which I will show you just in a minute, because the simulation itself will work properly. We set it to run in a single step simulation. The results will be calculating temperature and heat flux. After 5 minutes, the job is ready. The simulation was done and performed. We're ready to visualize the results. That's when we already had a sneak peek at the thermal results. We see a certain amount of temperature that is being transferred and the heat fluxes that are mostly moving the energy towards the board. But there's one element that got wrong in our methodology. And for this, I will have to show you again the simulation. Does any of you have an idea what was selected in the wrong way? Please raise your hand and start typing real fast if possible, so we don't have to wait too much. All right. Well, just not to keep you waiting, the problem was that we allowed the cooling to be happening on the top surface. And in this particular case, we're taking away 10 watts per square meter Kelvin. And also, if I hide these elements, I mean, I could hide all of them, you'll notice that the assignment is also taking away the energy from below the contact. That is not desirable. And well, we didn't think about this when we were making our first design and making it on Onshape. So let's see what can we do to repair this little trouble. So in this case, we have the trouble with the contact and we'll modify the geometry. Now, one thing is that I have created the geometry as an assembly. All these parts that are here have been selected and copied multiple times, assigned to certain connectors and positioned within the board. But I cannot simply select this little face over here and say, I want to split you using as a tool the existing parts, because my part studio looks like this. I just have a processor. They are not even positioned correctly. The resistor and capacitor are also separate entities, which later were bound together inside the assembly. And there is no direct option in which you can create a part studio. In order to work around, maybe there are some other ways. The way that I did it was that I exported this assembly as a step file and kept it as inside one of the tabs. It appears over here as one of the elements that you have in your assembly. And afterwards, I imported this body, flattening the uploaded assemblies as part studios. If you were not to use this option, you would get the part studios as separately and an assembly as a separate element. With the flattening selected, the import will look something like this. Each part, each element of the assembly was imported in Onshape as a separate part. And now, since we are within a part studio, we are allowed to use these elements and the faces as a tool to split the top surface of the PCB board and select a different connectors. Let's see how was it done. In this particular case, I created a new sketch on top of this body, and then I hid the board, at least for a sec, rotating it around. And then within the sketch, I simply used intersection elements such as these faces, each of those faces, to create the sketch, which will look, I'll try to hide all those parts if possible. Where is it? I believe that there was an option to view, but basically what we have are the sketches, and the sketch elements will hide all other parts, and now we have a sketch that consists of the element faces. And we can apply a split and split a face of our import one part board using the sketch that was done. Okay, so right now let's show everything once more. With this, we are ready to use the whole geometry immediately in SimScale. So let's go SimScale. To the mesh creator, we take a step back and import face, the geometry with faces. So just import from Onshape. There will be a little second before it loads. Yeah, you can see my designs. Very good. So I just select a PCB with faces split and import it to SimScale. As easy as that. This time we need to transfer the data. The files are getting big. It needs to be packed and sent. Within a second, everything is ready, and I can simply close this geometry. We could rename it. In fact, this is what I did. And if we take a look and invert selection in isolate selection, let's show only surfaces and pick faces, notice that right now the PCB board is also, the top face is also split into exactly matching faces that will be touching the electronics and everything on top of the body. All right, let's remove this little thing here. This is exactly the same geometry, which later we can mesh. In this particular case, since we are dealing with the pretty fine elements that need to be created, the mesh will be much bigger, and it will also have to represent properly the small faces on the PCB board. You can immediately notice that the mesh is much finer than it was previously, especially close to those little faces that are there. This will force us to use a new way of meshing that will be the tetrahedrization with refinements. In this case, I am using the maximum edge length to be the coarse mesh applied everywhere in the geometry, and a mesh, it's called mesh refinement, but basically it's making a finer mesh on solid zero that is the PCB board itself, so that we can capture those little faces that are on the top board. Having the mesh done, we can jump and prepare the simulation. So let's see how it looks like. Thermal simulation board. This time I decided to go with Codaster since, let's try it out. We select the PCB with faces. This is the mesh that was created. One tip for you, whenever you're dealing with this kind of simulations, the more little triangles the renderer has to draw, the slower will be the response rate. So I usually like to switch the view from surface with edges to surfaces so that the whole operation becomes much smoother. And it's easier to locate those little radiators over here. All right. Right now, there will be a little more work when it comes to creating the face sets, the topological entity sets, since we will have to select 33 elements on the electronics part and 32 on the board part. Okay, but after doing that, it becomes really fast since we can simply copy and duplicate the initial simulation. So let's do just that. We can duplicate the existing run, rename it, something meaningful as usual. Keep the analysis type. This time we are dealing with Calculix. This has to be kept in mind when we're doing that. And we change the domain to the next mesh that was created. As in the previous session, in this case, all the assignments disappeared. But since previously we made the selections, we can just select electronics to the board and board to the electronics. Notice that this time I should select the master to be the electronics, since they have a coarser mesh on them, while the board to electronics is the slave. In fact, it really doesn't matter which one is which for simple simulations like this one. When you get some curvatures or real contacts with stress analysis, that's when it becomes crucial to know which part is master and which part is slave. All right, and then next thing will be simply to assign the volumes properly for the bodies and proper heat fluxes. But this was already done, and we don't want to waste too much time on this set, so we'll just take a look through it. In this particular case, I'm simply selecting the bodies without creating topological entity sets for the volumes. I directly select them and use add selection from the viewer. So we could do that. Pick volumes, we pick the two volumes, add selection from the viewer. There they are. If we would like to add some extra materials, right-click on the materials, add a material, new material. There we are. We change the filter type to volumes, pick the volumes that we are interested in to have the new material, and add selection from the viewer. Obviously, we will not do that since one volume should have only one material assigned to it. Otherwise, it will be just silly. Okay. We have the elements given their heat. We'll set the same value, the same heat sources for all the bodies to compare the results that we got when we had a single phase taking away heat also from the hidden part of the elements. Though this time the cooling will be happening only on this element. So let's isolate this selection, select assigned, and notice that right now, oh, I must have made a short mistake. This also should be deselected, but hey, this is plastic to plastic. Nothing wrong will be going on. All right. For the result control, I keep the temperature and heat flux running. And this time we have a little longer simulation since we have a finer mesh and it requires time to calculate. We could go to the post-processor and simply visualize the results. Very often, for those of you who haven't seen this presentation, very often we have the problem of people calling us, why I don't see anything in the post-processor? Well, let's select the thing that we want to see. In this case, solution fields of thermal board run number 1. After a second, they will be ready for us to view. There we go. And we can, for example, color the thing with temperature. Obviously, we would like to see the scale, be able to notice what is happening. And we're expecting to have a higher temperature in the case where we remove the heat losses from below the processor. So we have 329 degrees Kelvin. And if we were to compare them to the previous run, which we can do right away, I'll just jump to the results. These are the results from the corrected simulation, and we have 330 degrees. Whereas if we jump back to these results, we see that there is 320 degrees. So there's like 10 degrees difference, which for a pretty well optimized PCB board can be a problem. And this was only obtained by selecting proper contacts and having the heat removed properly, not from below the elements. So we notice that this is pretty important. And also the heat flux happens between the electronics parts, and there is a lot more heat moving from the processor to the PCB board and later being dissipated by the convective heat transfer boundary condition outside. All right, but this was all fine. We just set up a proper simulation that was not optimizing our design. Let's add something more to our element. And let's start by creating some radiators. The first thing that I did, obviously we already saw the result, was to create a new part studio in Onshape and import the two processors, or the processor and the little chip, on the board. On them, we first create our initial sketch, that consists of several lines that were drawn on it. We have certain distances, let's say 2 millimeter thick, distance between them will be 3 millimeters, same distance from the sides. With the sketch ready, we make a second sketch on the second processor. Further, we go to extrude both of the bodies, and now I can also hide the chips because they are not important anymore. This extrusion will be just 4 millimeters up. Again, we can play around to optimize the design using different types of heat exchangers that will be created. And we start adding the extrusions. I found out that it's better if you separately extrude those fins from one processor and from other radiator and add them to the bodies. In fact, I got a big slowdown when I was trying to do it at once. I played a little too much, throwing around, moving extrusions. Keep it step by step. And obviously, this kind of radiators do not look very appealing. Let's add a fillet to them, which will simply be 1 millimeter fillet on every edge that is on the top. And a similar thing was done for the second body, which gives us two very nice radiators. Now we can create a new assembly, which will consist of our parts that were derived from the part studio that was created earlier, and adding two mate connectors, fastened connectors on the between the radiator number 1 and radiator number 2. The assembly is ready, and we can import it to SimScale. So once more, we go to the mesh creator and import from Onshape. Not surprisingly, we have the radiators present, and this time we go for PCB with radiators since we need all the parts to create a mesh. I will not click import since it's already been done. Here we have the PCB with radiators, and just to confirm that everything is selected properly, let's isolate our PCB board, show the surfaces, and pick the face and see if we did remember to use the proper PCB that was already split with the top face. All right, so it immediately shows, yes, there are different faces for each and every electronic contact that will be present in the system. We can show everything back again and create the mesh. Once more, we are using the tetrahedrization with refinements with a general pretty coarse mesh that is created on most of the elements and a refinement done on the PCB board itself in order to capture those small little faces that are present on the top of the board. Okay, there we are. The refinement is here, and we can prepare our simulation. The steps will be exactly the same as for the previous job, except for one difference. We need to add extra contacts. Since in this case, well, we will be connecting the electronics to the board. That will be contact number 1. So electronics to PCB and PCB to electronics. Contact number 2 will be radiator 1 connected to chip number 1. And last but not least will be radiator number 2 connected to chip number 2. These are bonded contacts, everything is glued together. And one more extension will assign the materials to all the bodies, including the radiators. Most of the time they are made of aluminum. It's a nice conductor, works fine. With the heat fluxes, we go with everything. And now I would like to share with you a little trick that I use for selecting all those faces that are done. Well, in order to select all 300 and something faces, that will be a real tedious job. So to do that really fast, after you created your topological entity sets, we'll have the face sets like that. So all the electronic contacts, the chip contacts, and radiator contacts, we can simply start hiding them. Obviously, nothing will happen on the screen, but believe me, they are being hidden. Simply, we are not being able to visualize this fact. Oh, now I also hid the top board. So let's show again everything. So start hiding, hide, 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 hide. So all the elements except for the outside walls are hidden. Now I can go here, clear the selection just to make a demonstration, and select everything that is visible, add the selection from the viewer, and check at the end, are we missing some faces? And indeed we are. These are all the connector faces between the elements. So we have just assigned a wall cooling, a convective heat flux to everything that is touching air. Obviously, you could diversify, since different materials will have different heat transfer coefficient if they are touching air. But for the sake of this example, we just keep it uniform. The simulation again took some time. We have even bigger mesh and even more contacts. And the results are pretty interesting. We definitely see the drop of the maximum temperature by 20 degrees. Again, we improved our design, taking away heat from the chip and moving it towards the radiators. The heat fluxes definitely are moving towards the radiator, and this is where the energy is being transferred and taken away from the system. All right, so what did we obtain? Definitely we have a temperature field, and another improvement that we can give in a very fast time to our colleagues and business partners and improve their designs. Now, this was just a single example of a radiator. We could start imagining what would it be like if we change the shape, add some strange geometries that will remove heat, increase the length of the fins, or even change their positioning. That is another interesting thing. Let's talk a short view of the benefits that you get from SimScale, and obviously from also using Onshape. Everything is going to be to develop your products faster. We do not have to burn 20 processors to get to know that, hey, I need a radiator on it. We paid for what we used. The simulation time, only the simulation time was used, and if you run public projects, it's all for free. We have great flexibility, possibility of sharing knowledge with others, and the security of the cloud for our data. All right, so these are the general things that SimScale can offer you. We talked a bit about structural mechanics, and today we had a look at the thermodynamics of the problem. Next week, we will take a look at the CFD aspect of the whole project and perform heat transfer analysis, buoyancy-driven flow inside our boxes, and even better, we'll make a two-step conjugated heat flow when we'll take the results from today's simulation on the board, and we'll apply them as boundary conditions for the fluid flow simulation. All right. Well, I'm perfectly on time. Last time, during last session, there were a few questions that you wanted to ask, so I would be happy if you would raise your hands and start typing so that we can talk a little bit about the designs and the possibilities combining Onshape and SimScale. So please go ahead. Oh, sorry, that was not intended. There we are. Yeah, I see some questions appearing. So please start using the chat tool. Takes a while. In the meantime, as you're typing, let's try to visualize the way of showing results in the online post-processor, because this is most of the time the interesting part for us to do. And when the questions will appear, we'll take a look at them and address them. Okay, so we have the heat transfer coefficient here. This is the temperature thing. I already created several screenshots for this, and all of them were done on the online mode. All right, so there's the question. The first one: are all simulation types available in public mode? Yes, they are. Everything you want, you can simulate in the public mode. You can. The only thing is that, well, you will be sharing your knowledge with all the community. So anytime you want, just create a project, use all the tools available that are under the simulation types. So let's take a look. So we have fluid dynamics, incompressible, compressible, convective heat transfer, passive scalar transport, multi-phase flow simulations, discrete phase models, and potential flows. We can also directly upload open foam cases if you want to use some specific solvers. For solid mechanics, we have static analysis in 2 versions from Calculix and Codaster. And again, dynamic analysis from Codaster and Calculix, model, frequency, and harmonic analysis that were covered last session. Thermostructural allows us to do uncoupled thermomechanics analysis and uncoupled thermomechanical analysis advanced. This is, again, the advanced always stays for Codaster, whereas the standard one goes from Calculix, which provides also pretty good results, but a little less functionality. There are eigenfrequency acoustic analysis for wave distribution inside closed volumes, and particle analysis, which is a discrete phase model. These were just the simulations, and the amount of models available inside is pretty big. Where let's cover also the meshing possibilities. Whenever you create a mesh, you can, let's just create a new mesh the geometry. We have fully automatic tetrahedrization. This is what was used right now with all parametric tetrahedrization. We can also create viscous layers and some refinements. Further, there is the hexahedral mesh generator, snappy hex mesh, which is used only for fluid flow analysis. Okay, there's a second question. Oh, this is just some sharing. I'm really happy for that you may try to go with FEA for your clients, but I'm sure that There is a question, do I feel that a regular mechanic engineer can gain enough confidence to make good analysis? And the question is, how do I know that I haven't missed some important part? Well, obviously, this will come from experience, and you will have the need to pay extra attention whenever you're dealing with this kind of simulations. At the same time, you have the access to the public projects, and this is a great source of inspiration whenever you're dealing with advanced simulation types. So, for example, we would like to make some stress analysis of a complex part, let's say a consumer snap fit analysis. This was a really good one. We have a snap fit, and we can take a look what was done by Richard, the way that he meshed it, prepared the parts. Another question. Let's just finish this one. So you have always the inspirations available. And then there is the forum where you can ask for help. We definitely are taking the attention, and there's a lot of people who would like to help you with your projects or will give you insights, asking, hey, did you include the contact? What did you use for master or slave? Or did you consider certain non-linearities that are present in the system? Okay, let's see further. Do we have access to the input deck file, txt? Right now, in order to, I'm not exactly sure what do you mean by that, but when you try to make simulations and perform any kind of analysis, when you import the geometry, well, you can do it from Onshape, and this is what we highly recommend, obviously. Then you could also import meshes directly if you create them on your local computer. Now, you would like to see a file which is run. This is a good point. So basically, you can download the results. We are storing them in a specific format that later is being translated to the solvers themselves. So for structural analysis, after you have the results done, you can just click and download them locally on your machine. They will be presented in a VTK format, as far as I remember. Whereas for fluid mechanics simulations, especially the ones done using OpenFOAM, they will be presented in OpenFOAM format. Then both of them can be visualized using the offline post-processor that we recommend, that is ParaView. There is a direct link in the post-processor over here. We're also using ParaView as an engine for the online post-processor. Oh, there's a question. I mean the text file, another refinement. So I mean the text file which is transferred to the solver, not the file with the results. So yes, for the structural analysis and heat transfer analysis with Calculix or Codaster, you do not have access to those files. They are directly meshed up, packed, and sent so that you get the results. For OpenFOAM, you will get the full structure of the case with the mesh, with all the files that create the simulation. Okay. The next question is, do you consider the resistor's heat generation? How would you do it? It was considered. In these simulations, I just made it really small. So let's take a look at the thermal board with radiators, the most advanced simulation. And if you go to the heat flux, there is the resistors part. I simply put too small amount of energy into them. This is just a fraction of a watt for cubic meters. So let's surface, but definitely there was some heat present there. And if you had a look at the results in the post-processor, I will just show them heat transfer. So this is the, okay, here. So you have the heat flux coming away from the radiators to the PCB board. And this means that they are connected and there is a certain amount of heat transferred through those rods. Okay. So another point when it comes to the input files, that there, without access to the file, there's no chance to check the job setup. Pretty dangerous. Well, I wouldn't say that this is dangerous. Well, you have access to the full job setup over inside the graphical user interface that was presented here. So you just go and check if the settings are the way you desire them. We provide you with the graphical interface and make sure that everything is transferred in a proper way. In case you would like to make sure that the job we are doing is good, I highly encourage you to go to the documentation and see the validation cases that were performed on SimScale using some the standard testing, and the validation is done against scientific papers. So we could thermal simulation, heat transfer around the sphere, all the results compared with the ones. So the whole idea is that we will take care of the files and make sure that you don't have to deal with this. The next thing, is the presentation from last week available, and will it be available for viewing? Yes, it will be, or we're going to release them most likely in a bunch together or later this week, depends on the way that we will require them to process or not. But for sure, you can and you will have access to them. All the webinars that were presented are, if we go to the SimScale Engineering, our main web page, learning, workshops and webinars. Here you can find the recordings from previous sessions and other webinars that were done. Also, you can go to our YouTube channel. We're uploading videos at this with the sessions. Oh, and you can already see it. Yeah, I even didn't check if my colleagues uploaded it. It is available online on the YouTube channel, SimScale GmbH. Okay. Okay, again, we're getting back to the input files. So you don't know what system writes into the input file. Do you plan to give access to this in the future? I have to state again that in general, we are taking care of writing exactly the things that you're putting in those little brackets to the system, to Codaster, to Calculix, and so that you don't have to deal and check 300 text files that sometimes are required to set up the simulation. So the whole plan is that you do not have to play around with it. And we do not foresee to release it, at least not in the near future. All right, any more questions? I would appreciate if you have a question to raise your hand so that I'm aware that you're typing. I know that it takes a little bit of time to put your thoughts on the keyboard. If nothing more bothers you, I would like to thank you for this session. As I mentioned, the recordings will be available soon online, definitely on our YouTube channel and later on the webpage. If you have more questions, go to the forum, the SimScale forum, and type them. We'll be happy to answer. You can also try to contact the support directly, and let's start simulating things together. Thank you very much for your attendance, and on behalf of the whole SimScale team, I wish you a great rest of the week. I hope that we'll see each other for the next week's session, where we'll discuss the CFD and thermal analysis. Once again, thank you very much. Paweł Sosnowski, signing out. Bye-bye.